If you are just joining us, my name is James Skelton. I'm the evangelist for Paperspace, and today we're going to be talking about YOLOv7. I'm sorry, I got a question asking if they can make it full screen. Is it not full screen right now? It is now. Okay, just making sure. Thank you for that prompt answer. Today we're going to be talking about YOLOv7, the state of the art in object detection. Before we get started, there's just a few little housekeeping things to talk about. If you're not familiar with who we are, Paperspace Gradient is a platform for building and scaling machine learning applications. You can explore a new library or data set in a notebook, automate pre-processing, training, or testing with a workflow, and bring your application to life with a deployment. I encourage all of you to join our community of over 500,000 users on Gradient today. And before we go any further, I need to make sure that everybody that is attending that wants to follow along has go ahead and created an account in Paperspace Gradient. You can do that by going to paperspace.com and then go to Gradient. I'll actually walk through this real quick. Excuse me. So once you've logged in and created your account, go to consult.paperspace.com. And then once you're in there, make sure that you are in Gradient by clicking on this Gradient symbol in the top left. Oops, that's my GitHub. Then navigate to the Notebooks tab. Well, actually, I take that back. Excuse me. You don't need to do any of this. You just need to make sure you don't need to do anything except for make sure you have a free account. Excuse me. I forgot my own steps. So once you've logged in and created your account, all you need to do to create the notebook is click this link here in the slides, and I'm going to share both the slides and the link now. Is everybody able to read my chat? Yes, okay, so you can get that link. Okay, just making sure. If not, I would have emailed it to you all right now. And here's the demo notebook. So all you have to do is click that demo notebook link. Click it twice, and that will take you here to the notebook page. The Google link. Excuse me. Thank you for the heads up. You should now be able to access the slides link. Sorry about that. Then using the other link, the second link, the one that ends in free GPU. To get started, all you need to do is click Start Machine and then click Private Workspace. And that will open a free GPU in your private workspace notebook with all of the code you need to run this session. I've already done that, so I'm not going to. One more thing to note is there may be a limited supply of free GPUs. If it tells you that you are unable to start up, I suggest coming back later. Later in the day, maybe later after the workday, there will almost definitely be availability then. You should be able to follow the steps naturally in the slides very easily. Mohammed, can I get you to refresh that? I just changed the permissions on the slides, so you should be able to access it now. And it looks like everybody's in here. Cool. Thank you, Paul. Thank you, Mohammed. All right. Then all you need to do is, like I said, hit Start Machine to start spinning up your notebook, and it'll be set for 6 hours, and you'll be able to run it when we get started. It may also be helpful to run this first cell. This has our data. This is a useful library for getting things from Google Drive. This is a video we're going to be using to show the results of our model. And this is a pre-trained model you can use to just do that without having to do any training on your own. And finally, this is the training version of the model provided by the original YOLOv7, excuse me, repo that we're going to train on. So it's the untrained model. It's a good idea to run that cell and this cell to go ahead and get your environment set up. You could also run these helpers. These move the data when you run that top cell, it'll dump everything into a train, test, and valid folder. This renames those files and then moves them into the right places for coding when we get to training. So all you need to do is run these first 4 cells to get your setup done. The YouTube channel, I got a question asking about the YouTube channel. The YouTube channel is named Hello Paperspace. Ahmad, if you are getting an out of capacity error, I'm so sorry about that. We have a limited supply of the free GPUs. If you would like, you can use one of our paid GPUs, like the P4000. If you would rather wait for the free GPU, there will be availability later. But because this is such a large session, I suspect that we are taking up all the capacity right now. So I really apologize for the inconvenience, but you should be able to follow along with me as we go through it here and then recreate it later. As I said earlier, I will be sending out a recording of this as well as uploading that to YouTube. So yes, once you've spun up your notebook and run those first 4 cells, you should be good to go for everything. And without further ado, let's jump into the theory. Okay, so as I said, we're going to be talking about YOLOv7 today. In order to do that, I thought it would be best to introduce object detection first, and then go into the history of the YOLO model, explaining how the original YOLO worked and its architecture. We'll then move on to exploring how YOLO has evolved. So YOLO2, YOLO 9000, YOLO v3, YOLO v5, seeing the changes that were made in those architectures that allowed the new versions of YOLO to outperform the previous. Yes, I can write down the channel's name. The YouTube channel is at Hello Paperspace. And that is, just put that in the chat. Okay. Finally, we will, oh, that's a typo. We're not talking about the use cases and applications for YOLO. Those will be apparent throughout. We'll talk about what's new in YOLOv7 and then jump into the code demo. All right, without further ado, let's talk about object detection. Really quick, it's not showing on my screen. Can I get another confirmation that you are all seeing the full screen? Yes, thanks so much. Yeah, normally Zoom has a green thing around it. Okay, so object detection. Object detection is a computer technology related to computer vision and image processing that deals with detecting instances of semantic objects of a certain class, such as humans, buildings, cars, etc., in digital images and videos. And here's a screenshot from a tutorial from contributor Ayush that we have, where it shows different classifications for cars, buses, traffic lights, and people, and handbags. This is from the original YOLO, which is why we're not seeing probability numbers next to it, but you'll see how much this has changed as we go through these sessions. Object detection can be thought of as the union of 2 computer vision subdisciplines, object localization and image classification. Object localization is the ability to recognize multiple objects' positions in a single image. So here we can see that it's detecting multiple objects here. And then to add the labels, image classification allows for the identification of the class label for these objects. When we unify these and take it further, we can get object detection and eventually image segmentation. So there are 2 main object detection approaches. Tim asked a good question. Does one happen before the other? In YOLO, they are simultaneous. And I'm going to actually get into that right now. So object detection has 2 main approaches in the school of object detection, I suppose. They're single stage and 2-stage object detectors. And in this graphic I have here, A represents the single stage versions and B represents the double stage, or 2-stage, I should say. Single stage object detectors treat object detection as a regression problem. An image is input directly to the network, and it then outputs the class probabilities and bounding box coordinates. A 2-stage object detection relies on the region proposal stage. This stage identifies regions that could contain objects and then passes those on to the classifier. So it takes from the feature map, proposes the regions, and then uses that to make the classifications. Single stage is generally faster, but two stage is considered generally more accurate. YOLO is single stage. So to clarify my answer to Tim, who asked, does one happen before the other when referring to object localization, image classification? In YOLO, they are simultaneous because it is single stage. So let's jump into YOLO now that we are familiar with the background. YOLO was introduced by the paper You Only Look Once, Unified Real-Time Object Detection in 2015 by P.J. Reddy or Joseph Redmond et al. They aimed to devise a method for a single neural network to make predicted bounding boxes and class probabilities for objects on full images in one evaluation. Since the whole detection pipeline is a single network, it can be optimized end-to-end directly on detection performance. It was the first approach that treated object detection as a regression problem and represented a significant step forward in object detection technology. It's since gone a lot of advancements, and its successors have remained some of, if not the de facto top performant models for object detection. And this is kind of a small image, and I apologize for that, but we can see here roughly the main idea of how YOLO is working on a very broad level. It's resizing the image, running the convolutional network to find the features, and then using non-max suppression to remove the lower probability predictions. I'm going to go into what I just said means in a lot more detail in just a moment. So here's the part that I think everybody's most interested in. How does YOLO work? Well, first, like any machine learning or deep learning framework, the model requires labeled, well, I should say supervised framework, excuse me. That's a typo. Any deep learning supervised framework, the model requires labeled data to train on. These labels correspond to a series of bounding boxes and classifications. Most often, these are labeled manually by a human user using a software like LabelMe or RoboFlow. I chose to use RoboFlow for this, and I recommend you use RoboFlow as well. It's a really nice piece of service, and it has augmentations that can change the way your images look, which can make your YOLO model more robust, and it can also triple the size of your data set by tweaking those augmentations and making different versions of the same image. This will make your data set a lot more robust, and I definitely recommend you use that and take advantage of those augmentations. YOLO then learns during training to be able to predict those classification and bounding boxes on objects, and the loss between the predictions and the real images allow the model to iteratively improve its predictions. Over here on the right, I've just got a little GIF showing the process on RoboFlow for labeling data. I'll show you all the RoboFlow website and the data set in a little bit. Oh, excuse me. And we can see here that it's first labeling this player. Then I'm dragging my bounding box here and changing the classification to ball handler, and then doing a similar process to drag and then change this one to player. So this is how you manually identify and label different objects within your images for YOLO to learn from. Okay, so part 2 of how YOLO works. One moment, please, sorry. Okay. YOLO works to perform object detection in a single stage by first separating the image into in grids. So we have our in grids here. Each of these grids is of equal size S by S. Each of these regions is used to detect and localize any objects they may contain. For each grid, a bounding box coordinates B for the potential objects are predicted with an object, oh, excuse me. Oh, all right, sorry about that. For the potential objects are predicted with an object label and a probability score for the predicted object's presence. From there, as you may have guessed, this leads to a significant overlap of the predicted objects from the cumulative predictions in the grids. So we got a good example of that here in this image. So it will try and make a lot of predictions, and then it will use those with a process called non-maximal suppression to handle the redundancy and reduce the predicted objects of interest down to what we are really looking for. Using these probabilities and confidence values, YOLO is able to narrow the detected objects down to those above that confidence threshold. So this image here is a representation of that process. So we start off with these S by S grids. These kind of represent the exact same thing. Then we produce a lot of bounding boxes and with confidence, and then we reduce the set of bounding boxes down to those who pass a certain confidence threshold to get our final detections. As we can see here, it's predicting, I'm guessing, a dog, a bike, and a car. Yes, okay. Got a question. I have two good questions, actually. Could you explain what S by S is? Is that a configurable value that can change accuracy but reduce speed? I'm not actually sure. I haven't gone into too much detail with the hyperparameter tuning personally. My assumption would be that yes, that is something you could tune. But S by S just represents the pixel size of the in grids. My assumption is that if you were to lower the size of S by S and therefore create more grids, that would slow down your model training time and inference time, but probably greatly increase its ability to handle smaller objects. That being said, that wouldn't be a good idea on low resolution images. So if you were toying with that idea, maybe work with a very powerful GPU in 4K images or something like that. Next question, how do I handle occlusion? That's a really good question. YOLO is actually optimized to handle occlusion simply by dragging over. So I actually can pull up a quick example of this from our data set. And this is just useful anyway maybe I can show how to hand label really quick. So here are some images. Just for the record, I took these off random YouTube videos. Just try and find one where a player is being blocked. Let's see. Okay. I think we can assume that he has the ball based on where this footage is. So we can drag over him. And I would call him the ball handler. And then if you're dealing with occlusion, you simply pretend that the other label isn't there. So I would label this player in front of him the exact same way. And YOLO learns through the multitude of occluded images that it sees how to deal with occluded images. Because if you look at this data set, more often than not, players are bunched up on each other. So we'll have a lot of situations where I'm creating bounding boxes like this. And as it gets experience with more and more data like this, it is able to handle that occlusion. Next, does freehand labeling improve performance rather than rectangles? I would guess so. I haven't tried doing it in that way. I imagine that would increase the complexity of the bounding box prediction significantly. If you were trying to do something like full body detection and then in painting where you would remove the body, you would want to use the software like FGT. I don't think that corresponds to this. That seems like it would be. I think the rectangles is the way to do it. When I say freehand, I just mean manually doing it. There may be a methodology for more closely outlining the objects of choice, but I haven't seen it. Thanks for the good question, Mohit. If an object is completely occluded, but you can assume it would be there based on external factors, would you personally label it still? Yes. That is a really good question. I would not if it is completely occluded. If there's even some of it showing, I would label it. But if we had two basketball players standing like this and you could not see my hand behind, I would not label the behind hand. If they were standing like this, I would. So use your best judgment on the occlusion. I think if you had enough data and it was completely occluded, then that would be viable. But it is asking a lot of the model to learn that connection. For now, my recommendation is to just use your best judgment. Okay, let's get back into the slides. Will classes be manually labeled in the whole data set? Yes. You define the classes yourself in the data.yaml file, or coco.yaml is what I named it. Basically, it takes a YAML file to know what classes there are, how many there are, and where the data is. And that goes into your detect, train, or test scripts. We will get into that when we get to the demo. Okay, next. Got a bunch more to get through, so I'm gonna move on now. The YOLO model is made up of 3 main components to handle what we just described in the last slide. These are the head, neck, and backbone. The backbone is where the convolution layers detect the key features of the image for processing. This is typically pre-trained on a classification dataset like ImageNet, so it's very robust. The neck takes the features from the backbone into fully connected layers to predict the bounding box coordinates and classification probabilities. Finally, the output layer is the head. It takes everything together and then generates your image with the bounding boxes. It can be interchanged with other layers with the same input shape for transfer learning. And here I have an image from YOLOv7 showing what that process looks like. YOLOv7 added 3 different scales, which is why it has this output at 82, 94, and 106. But that's what's happening there. All right, part 2, YOLO architecture. Here I have a diagram from PP YOLO, which is one of the versions of YOLO that followed after Joseph Redmond left AI. As we can see from this diagram, the backbone extracts the features from the input. These are then organized into feature pyramids by the feature pyramid networks in the neck. Feature pyramid networks are feature extractors that take a single scale image of an arbitrary size as input and then output proportionally sized feature maps at multiple levels in a fully convolutional fashion. The top-down pathway hallucinates higher resolution features by upsampling the spatially coarser but semantically longer feature maps from higher pyramid levels. These features are then enhanced with features from the bottom-up pathway via lateral connections. Each lateral connection merges the feature maps of the same spatial size from the bottom-up pathway and the top-down pathway. The bottom-up feature map is of lower level semantics, but its activations are more accurately localized at its subsample fewer times. These features are then taken from the feature pyramids to the head, which is the YOLO layer, and that is used to compute the cross entropy for classification, the L1 loss for bounding box positions, and the objectness loss, which is then used to iteratively improve upon YOLO during training. All right. Finally, we can see how it all comes together. The model is capable of detecting the presence and classifications of the desired objects within the image data. And as we can see from this example, it's able of discerning the presence and identifying the label for each of the 2 types of basketball players currently on the court, despite the model not having ever seen this footage before. So on the left here, I have the original input video. Again, this is just a sample I took from YouTube. I think this is footage from 2019. I trained all my footage on, excuse me, did it again. I trained the model using footage from this year. So a good test set would be older NBA footage if you're looking to test out your model, show how it works. But yeah, it does a pretty solid job. As you can see, it is mostly able to tell that that is the only ball handler. There's an occasional confusion. Sometimes it is detecting a ball handler over here, or it is not labeling all the players on the court. This could all be solved with more data and more training. I'm using a relatively small data set just for the sake of not spending 20 hours hand labeling the images, but it's still pretty robust, and I'm happy with the output. Okay. Before we dive into YOLOv7, I want to talk a little about how YOLO has changed in between the original YOLO and YOLOv7. YOLOv2 was the first to follow YOLO and introduced batch normalization, which was able to raise the mean average precision as much as 2%, and anchor boxes. Candidate anchor boxes allow inference to work on multiple objects in the same cell. Basically, it allows the mess of boxes, kind of like we saw in this sample image here, to then be used to detect multiple objects within one cell by defining these anchor boxes. And then it will choose the best probabilities, and altogether, this has increased the total objects it can detect per cell to 5. Up next is YOLO9000. YOLO9000 merged the class labels from ImageNet with COCO, which allowed for over 9,000 labels to be classifiable by YOLO. Prior, it was only able to detect the, I believe, 80 labels set by COCO. This kind of creates a super network of labels where the higher level labels from COCO can then be used to organize the lower labels from ImageNet and so on. So YOLO9000 provided an interesting step up for the ability to do more diverse classifications. Next is YOLOv3. YOLOv3 used a much more complex DarkNet 53 as the backbone. I believe the previous one was DarkNet 26 or something like that. And a 106-layer neural network, excuse me, turn on Do Not Disturb. Sorry about that, everybody. Yes, sorry. It uses a 106-layer neural network complete with residual blocks and upsampling networks. In practiv, this allowed YOLOv3 to make predictions at 3 different scales, with the feature maps being extracted at layers 82, 94, and 106 for these predictions. If you recall, earlier I mentioned this about the YOLOv2, so it's able to extract at these different levels. This significantly improved the model's ability to detect small objects, and I neglected to put this in, I'm sorry, but it also reduced the number of objects it could detect per cell. That is the the S by S cells in grids, down from 5, like in YOLOv2, down to 3. That trade-off was considered acceptable because the performance wasn't reduced significantly, and it was able to detect on much smaller objects. This was the last of Joseph Redmond's official YOLO models. Since then, the torch has been passed on to various open source developers. One company I recommend checking out that has been working on this is Ultralytics, who have developed YOLOv5. YOLOv5 represented a really interesting step forward for YOLO because it used, well, first of all, it's the first PyTorch release. So since PyTorch is so ubiquitous now, this helped a lot with making it more easy to use for people. Next, it used a cross-stage partial network backbone and a path aggregation network for the neck. A CSP net, the cross-stage partial network, solves the problem of repeated gradient information in large-scale backbones and integrates the gradient changes into the feature map, thereby decreasing the parameters and flops of the model. If you're not familiar with flops, that's the floating point operations per second, which not only ensures the inference, ensures a higher inference speed and accuracy, but also reduces the overall model size. The path aggregation network, or PANet, adopts a new feature pyramid network structure with an enhanced bottom-up path, which improves the propagation of low-level features. At the same time, adaptive feature pooling, which links feature grids and all feature levels, is used to make useful information in each feature level propagate directly to the following subnetwork. PANet improves the utilization of accurate localization signals in lower levels as well, which can obviously enhance the location accuracy of the object. So those are the architectural changes. In addition to that, it also allowed for automatic computation of anchor boxes when you're using custom data. This is really nice. Prior to that, you had to specifically manually define the anchor boxes. And it also allowed for mixed precision training of models by adding FP16 processing support. So YOLOv7 represented a very, very nice step forward, and I definitely recommend checking it out because it is definitely the most user-friendly and most taken care of the YOLO releases. Ultralytics takes really good care of that repo. So if you are looking to study YOLO, I actually would recommend starting with YOLOv7 instead of the bleeding edge with YOLOv7, like we're going to be talking about today. That being said, you should be able to use everything we're doing anyway. All right, finally, let's talk about YOLOv7. What is new? So in addition to all the changes I listed from the new versions of YOLO from the original, YOLOv7 also features an improved backbone convolutional layer called ELAN, which is this far right option. This new computational block does not change the gradient transmission path of the original architecture at all, but instead uses group convolution to increase the cardinality of the added features and combine the features of different groups in a shuffle and merge cardinality manner. This way of operation can enhance the features learned by different feature maps and improve the use of parameters in calculations. We can see here how it does that. Pretty complicated. Next, they added an updated model scaling technique. They scale the network depth and width in concert while concatenating layers together. And they found with ablation studies that this technique keeps the model architecture optimal while being able to still scale to different sizes. We can see here on the side, this is what that scaling will look like. If you simultaneously scale both the depth and width, then excuse me. I've lost my train of thought. Basically, if you were to scale the depth or the width, that could cause problems with using your different data. So this method allows for more complex data inputs. Sorry. Next. Module level reparameterization techniques. So YOLOv7 uses gradient flow propagation paths to see which modules in the network should use reparameterization strategies and which should not. Here's just some examples. As you can see, this rep planenet, P1 rep resnet, P3 rep resnet, P4 rep resnet are the examples where reparameterization strategies would be used. And finally, auxiliary head coarse to fine. The auxiliary head does not train as efficiently as the final head because there's less network between it and the prediction. So the YOLOv7 authors adapted a coarse to fine definition where supervision is passed back from the lead head at different granularities. And we can see here in E what that looks like. So it's passing the head here, but the lead head is also being passed to the loss. All right. Well, without further ado, that is all the theory. Now you can go ahead and go back into that link we opened at the start of this call. And if you have not already, or if you missed the start, I'll just quickly talk through this. This is our notebook. I'm doing an MBA 2 just because for this example, I've created a second version that runs more quickly on a bigger data set. So keep in mind, that's why the name is different for the file. What this first cell does is it downloads our data set, which is from here from RoboFlow. Basically, all that's doing is we've got these versions. So I'm taking an export and copying and pasting that. So very, very easy to get your data from RoboFlow. And since the internet is so fast in the data center, you'll have this all set up really quickly. Next, we're installing GDown, which is a package that lets us download things from Google Drive. And then we're getting a test video and pre-trained model to use later. Finally, this is the training model from the official repo, which I should go ahead and link to. This is definitely worth checking out. I also have it linked in the slides, but just for now, I figured I'd put that in there. And when that's all done, you will get all your images extracted. One thing to note is, this is kind of a flaw with the free version of RoboFlow, is it appends this, I guess you'd call it a suffix, to all of our images and labels. To deal with that, I've added some helper functions down here that renames all of them so that you don't have to deal with that. Basically, the labels and images have different suffixes, so you can't run it directly out of the RoboFlow set. One last thing is it'll be labeled differently as vtest in your notebook. This cell here, which is actually just this one, this makes the directory that we're going to move the train, test, and valid data into. YOLO requires them all to be in one directory. It's just simpler that way to move them in there. So I opted to name it vtest. As far as requirements go, there is a requirements.txt file that we're going to install the packages from. We're also going to install setup tools 59.5 and this version of Torch Vision, which will also install Torch 10.2. 1.10.2, excuse me. Once that is all set up, I got a question. Does V7 do anything new with semantic segmentation? I'm not positive off the top of my head. I'm going to save that answer for the end of the session, and I'll try and look that up while we're still here. Thank you for the good question. So once your data is all set up, you should be able to see it over here on the left in this vtest folder. If it's not showing up, just hit refresh Explorer. It will. And then you can go ahead and look at it. Just a small test set of about 80 images, randomly pulled from the full data set, a much larger training set, and a much larger valid set as well. Okay. So here, what you are going to want to do, let me just check one thing. I'm on my A6000. Okay. Excuse me. That I was using my faster demo notebook. So this is actually the one that you are all working on, free GPU version. So in the train section, you should have this right here. This train.py takes a few different arguments. So we can define our workers as 8. Device is 0. That lets it know to use the first GPU, which should be the only GPU you have. We're going to use a batch size of 2. I know that's really small, but it's just in the interest of avoiding out of memory errors. Use coco.yaml for our data. That's just right here. Then image 640, 360, that's the image size. We're going to be using, small typo. If you have 7x right there, change that to 7. Sorry about that, everybody. Your config cfg/training should be YOLOv7, not YOLOv7x. Please excuse me, small typo there. I will fix that in the repo. Then for our weights, we're going to use the YOLOv7 training that we downloaded. I named this YOLOv7 ball handler, but you can name it however you please. And then finally, this hyperparameter script here defines our hyperparameters, and we're using 50 epochs. You can go ahead and start training now if you like. It should run. I've got it running now. It's been about 2 hours. You can see it's on epoch 10 right now. So it's very slow on the free GPU. If you would like it to be faster, I definitely recommend upgrading to one of our pro growth accounts. But one other thing to check out is this coco.yaml. This was originally to use Coco, which is why it has the name. I just opted to use the same name. I switched it to vtest/train for training, vtest/valid for valid, vtest/test for test, set the number of classes to 2, and then put in my class names here. Then for the hyperparameters, you can go ahead and change those here. Let me see. I wanted to see if we could change the size of the grid boxes by changing S here. And I'm not seeing that. So to answer a question from much earlier, it doesn't look like you can change the size of the S by S grid boxes using the hyperparameters. Oh, I have a request for an increased font size. So sorry. Let's zoom in. Is that better? Can I get a mod? Oh, assume it's better. Oh, I got a good question. How big is my training set? So my training set is 1.6-ish. It's 1,600-ish images, I believe. This is not recommended. I recommend a much larger training set for this kind of task. I think the recommendation is 2,000 images with very clear classification labels for each class in your training set. And then about 20% of that size for the validation set and 10% of that size for the testing set. That's convention. I use a smaller set just for sake of ease, but you could even go and take what I've already done and expand upon it by adding more basketball player footage. Okay. So once you have got this all training, oh, excuse me. Yeah, once it's what in the world? Sorry, everybody. I thought I'd must have gotten confused. Yeah, okay, go figure. Once you've started the training and run the training, you should get a final output that looks like this. It'll output your total images, total labels, the precision, the recall, the mean average precision at 0.5, and the length of time it took to train. It'll then output the last model it trained, so the last version and the best version. So throughout, it was saving the best versions, and if it found a better one, it would replace it. So if you go into the folder called runs here on the left, and then train, you'll get a series of folders containing your model weights and some helpful little images. So this is from the test batch. This shows what our training data was like and what it had to work on. We can also see how the actual labels versus the predictions here, along with the probabilities. It's got a precision curve, a precision recall curve, and an F1 curve. And finally, our model weights. You're almost always going to be wanting to use the best model, by the way. But occasionally the last will outperform that on a qualitative level. All right, so now if you've completed your training, and it is, since I did this on an A6000 × 2, that's why it was so fast. It'll be a lot slower on your free GPU, as I mentioned before. Sorry, I'm just, I thought I had one training and now it's no longer here, and I got confused by that. It doesn't matter. If your training is finished, you will have all of this, and then you can go to our next section, detect. Here I've got, you should have two different bits of code, one to use your model. Let's change this to best. So that will be in runs train YOLOv7 ball handler weights. And then we've got the video that we downloaded from GDown, which is testvid-nba.mp4. And I'm just calling this test. The image size for the video is 640. And then all you need to do is run the cell. And once the model has traced, which is essentially just saying start it up, it will start generating our predictions. Now, on gradient, we don't allow, I believe it's QXC is the name of the extension, pop-up videos. So, but if you were to do this on a core machine, you could add the view image, excuse me, let's type that, the view image flag here, and that would actually show, as the detection is happening, frame by frame, the detections in a live feed. So this is how you would use YOLO with a security camera or a live video. In fact, YOLO works with URLs. So we could go to youtube.com right now. And as you can see, I like games, and download NBA 2017 highlights. Okay, trying to find, let's do a short video. Oh. Well, that filter isn't working, is it? All right, there we go. So we got a Russell Westbrook highlight reel here. If you're not familiar with him, he's a pretty good basketball player. You can go ahead and take that URL and paste it where it says source. I'll wait for this to finish. Shouldn't be long now. Yeah, nearly done. And in the meantime, I'll answer some questions. Thanks for your patience, question askers. I just wanted to get through all of this. Franco, yes, it is faster than YOLOv7 and more accurate than YOLOv7. It is just much newer, so the documentation is less thorough. Notebook question. When something is looking for an input, is there any way to... Oh, Tim, if you're running into that, manually delete the file on the left using the file explorer. So you got that readme.dataset.txt, delete permanently like this. And then the readme.roboflow.txt, delete permanently. And then I believe there was one data.yaml, delete permanently. Then you should be able to run that and it will download. Are these predictions per frame of the video? I believe so, yes. Let's check really quick. We can go into detect.py and look at our arguments. Should be able to size object threshold. Yeah, okay, just judging by this, it's looking like it's converting the image. Yeah, it's converting the image to an image sequence and then taking for each image, converting that to a tensor and then doing that. So yes, frame by frame would be the likely answer to that question. So yeah, the predictions are per frame. Can we use ML to predict if Westbrook will be traded and where to? You can. I don't know how accurate that'll be, but you could definitely try. I know NBA 2K has been trying for years. Does this version work for instance segmentation? You know, I actually need to check. I'm not sure if they've, yes, okay. I have not optimized it, but YOLOv7 does work for it. it looks like just making a few changes, we could change YOLO to create masks. It was just out of the scope for this presentation. If you would like to use this for instance segmentation in inpainting, I'll throw this back in the chat. Definitely go to the original repo. And I'll go ahead and say right now, I'll make this one of my next projects to mess around with. There's also pose estimation, which is really, really nifty. When do you suggest to improve small object detection, such as tennis balls? Thanks. That's an excellent question. So let's say, I'm going to go ahead and assume we are talking about an actual like live footage. Let's say we're watching television and there is a tennis game going on and we want to be able to see the balls on the court. I would get the highest resolution images from those tennis games as I could. And then I would just follow the same strategy and label them. It should be robust enough that it can detect it. So for example, just for my own interest, I tried detecting the basketball prior to this, and I didn't have a particularly hard time, even though I was working with very low resolution image data. To clarify why that is, the higher resolution the image data, the more expensive computationally the training will be, as well as the inference. So in the interest of making something faster and more quickly recreatable, I used smaller image data. And if you actually go into my versions, you can see that I've resized all of this to 640 by 360 from the original 4K size. Oh, thanks so much for coming, Tim. I hope I didn't miss you. Anonymous attendee, I hope that answers your question about the tennis ball. What is the FPS rate of running YOLOv7 detection without GPU? So on a CPU. I don't have an answer, to be honest. I would assume it would be very, very slow. You know, the benefit of a CPU versus a GPU is that the GPU can make many small calculations, whereas the CPU is able to do single large calculations at once. Or I know that's a very strong simplification. But as a consequence, I think the CPU would struggle to handle the multitude of tasks that YOLO needs to be done concurrently. Let me see if it has a CPU implementation. Yeah, okay. It looks like they have CPU availability. I would say you're going to want to reduce your model size even, I mean, not model size, image size even further if you're going to use a CPU. But I don't know the FPS. Thank you, RH. Max SPS as something like Jetson Nano or OpenVINO. I'd have to look up the Jetson Nano stats to answer that. Let's see. It would be extremely slow to run training. Just looking at this. Yeah, my suspicion would be even slower than the M4000, but I'm not, for inference, I'm really not sure. Let me see. I just closed that, sorry. What's the word I'm looking for here? Not stats. Information about the product, whatever. Oh, specs, specifications, darn. Let's see. Yeah, at 4 GB of memory, this is going to be pretty slow. Let's see, we're working with, that's my A6000. We are working here on a M4000 with 8 GB of GPU RAM. So let's quickly use this as an example. Did I download the pre-trained? on here? I don't think so. One moment, this is an old version. Let me get my pre-trained model from here. Stick that on there. Oh. Lost my kernel. That's what happened earlier. I was wondering why it looked like the training had disappeared. Oh, okay. And then. So this is how you would run it on the pre-train. By the way, you would already have this. You wouldn't have needed to move that down. You would just need to go down to this detect section and change it to say bestbasketball.pt. That's the name of the pre-trained model that I've provided. And then we're running it on testvid.nba, which I have here. Let's see how it does on an M4000. And let's compare it with two A6000s. One last thing, if you want to get more statistical information about how your model is performing, there is this last section, test. Just so you're aware, I haven't determined exactly why, but the test script seems to run on the validation set rather than on the test set. So I provided this test.yaml as well, which just reverses the validation and test set file locations in the YAML script. And it will assess how good your model is on the test set. So very similar to that final output from training, but on unseen data. So I would use this detect to get a, as you, by the way, I stood here, you can see this is significantly slower. Oh, excuse me, I had, all right, well, I accidentally went back, so now it's gonna reload my page. I also had view image, which is why that wasn't working. So yeah. Let's see, is that still saved? No. Thanks for your patience, everybody. Okay. Let's see. Yeah. Okay, looks like there's some problems with the XTB platform working with the live video. So if you're going to run this with live video, like an HTTPS, RTMP, RTPS, you may need to download it first, or consider running your inference on a core machine. Core machines will give you access to a full desktop along with all of this, or you can SSH in, whichever you prefer. Okay. Sorry it took me so long to get to your question, Gerald. Do you know how large the subject should be in terms of pixel in the image to detect, to be able to detect by the YOLOv7? For example, if you want to detect some biological cells. That's a really good question. Obviously, YOLOv7 is a godsend for those of us with experience with fluorescence microscopy. Being able to label and identify cells using a computer is amazing. That being said, there is obviously a concern about resolution and being able to get that. I would say if the object is consistently visible to the human eye, you in the picture. So you looking at the picture on your screen, if you zoom in and it is not so fuzzy that it is completely alien, then I suspect YOLOv7 will be able to handle it. Those feature pyramid networks introduced in YOLOv5 were conserved in the YOLOv7 design and are very good at detecting the much finer features and propagating that up through the to the final output. I would say if you are working on biological data in particular, I don't know, let's say we're looking at nervous cells and you've got what's it called? A cross section of nervous cells, one cell thick. Most likely, just from my memory, you would still have enough detail that you would be able to identify. Well, okay, depending on your zoom, you would likely have enough detail to be able to at least identify the larger organelles in the nucleus, as well as possibly any like activation markers of interest that may have been injected into the cell. I think YOLOv7 would be sufficient. Sorry, super roundabout way of getting to that answer, Gerald. Are there any other questions? I see that we're 5 past, and I don't want to hold people any longer. If you are needing to go, that is completely fine. I just want to make one last note to everybody, which is to make sure you check out the links and resources, which is the very last slide. I have my original blog post there, as well as the basketball repo, the original repo, a breakdown on the original YOLO, a great article from RoboFlow and YOLOv7, which contains a lot of the same information as mine, and this breakdown on feature pyramids, which I found super helpful. That being said, thank you all so much for attending. I really appreciate you giving me your time like this. Be sure to give this a shot later today if you were unable to use the free GPU. It will definitely be available as people are ending this session. 60 people are going to be going off the free GPUs. I'm certain one will come up. As I said before, I will be sending out a recording of all of this to everybody that signed up for the session. So look out for that in your email, probably Monday. It will also be uploaded to YouTube at Hello Paperspace.